Hello, everyone. Welcome to session 7. We're exploring topics in agricultural robotics this afternoon. I'm super excited to introduce you to our first speaker, Mr. Clay Mitchell. He's a co-founder and managing director of Full Line Capital, an investment firm focused on both farmline and capital venture. Good luck.
Thank you. And thank you to the conference organizers. And I appreciate your bringing the sea people and the land people together in this conference. And all the sea people have been kind enough to not mention that land is only 30% over the Earth's surface, although it's been strongly implied a few times. So taking a little wind out of my sails, but nevertheless, as a registered advisor with a Security and Exchange Commission, I need to have a disclaimer that says that we're both best off if you don't rely on anything that I tell you today. So going very lightly here through a little bit of history to set context before I get into the kind of things that we work on today. I grew up farming in Iowa, fifth generation farm. And one of my early memories was as a 3-year-old watching my parents build a ham radio tower. My brother was 4, and my dad started teaching him physics and electronics, and he passed his ham radio exam at the age of 4. We were always programming at an early age, always building machinery. And so there was just kind of a love of farming and a love of building. And soil conservation was very important. So we're always looking at how can we improve our productivity while not tilling the soil. This is a picture of a fertilizer applicator we built about 30 years ago for injecting anhydrous ammonia fertilizer without disturbing the soil. I was one of the early users of survey quality GPS, RTK GPS for steering all of my machines. One of the things that enabled was using C3 and C4 crops that are good rotational partners, where the C4 crop is taller and higher value, and the C3 crop is shorter, lower value, placing them in close proximity and optimizing the crop canopy. So I created sun path diagrams for different canopy configurations and came up with the optimal configuration, and the automation really allowed us to execute that. Here's a picture of spraying in that system. I had some visitors from China that day. I asked if they cared to know what I was spraying, and they said, no, we're okay with it, whatever it is. One of the very impactful moments that I had early in the farming career came from this image. This was early in the cropping season, and the grass strip down the center is in the Midwestern United States. We call it grass waterway. It's a conservation strip for holding soil at the low point of the topography. And I noticed these vegetative paths 9 meters wide coming out of each side, and had not noticed that pattern before. It was giant ragweed, which is one of the bad weeds that we have in the Midwest. And so I started paying attention to how was it we were distributing that. Well, when we would spray drift was getting into these border areas, it would select for the weeds that were the most resistant to it. It would be harvested by the combine. The combine header bars, you'd raise it, would still be lower than the heads of the seed rain. It was around the time of harvest. And so around the Midwest, you see a lot of fields that instead of having like a healthy kind of grass that people want to see around the edge of fields, you have a giant ragweed, or you have, this is a picture of velvet leaf. This is a picture of our worst weed, water hemp. And this is a pattern I've seen all over the world, something that spray drift leads to. And so I've noticed that there's kind of a 3-year cycle that leads to this weed resistance. You've got deposition of the spray from the drift from the machine in the first year, selection, pressures, growing of the weed in the second year, and then dispersal by machineries that pick up around the edge in the 3rd year. And that observation, combined with looking at kind of a lot of errors that we were generating in spraying, led to some automation improvements that we made to our sprayer. So this image on the left is from Scott Shearer, who's at the Ohio State University now, and he wrote a paper saying that because of lag in control, spraying is one of the activities that has the biggest speed change. You generally plant at 5 miles an hour, a lot of other field activities around that speed, but you'll spray up to 20 miles an hour. And so those lags, as well as Spray booms are often 36 meters wide, and turning the inside of the boom can be going back over itself, and the outside can go 60 miles an hour. All of these errors, along with overlapping errors, cause really, really poor kind of accuracy within the field. And so one of the early innovations that we did, because we had RTK auto steering on our machines, was build on that positioning platform by putting individual rate control on every nozzle. So we'd have 3 nozzles, a low, a medium, and high. And so we could select low or medium, high, low and medium, medium or high, low or high, low, medium, and high, 7 different rates. And so we could have turn compensation, but also keep the pressure that would allow us to have the right droplet sizes. We would speed up and slow down through a wide range. And we also added speed compensation to the sprayer. So anticipation is a really useful thing in robotics, and what that means is a lot of just different contexts. But in a sprayer, you push the propulsion handle forward for the hydrostatic drive system and start speeding up, and then the machine senses you're speeding up, the sprayer pump speeds up, and sometime long after you've hit your target speed, the sprayer is putting on that rate. But we could use the machine state to very accurately predict, when we would push that propulsion level forward, how fast we would be going in a few seconds. So the response of moving the propulsion handle is going to be very different if you're on hard ground, soft ground, going uphill or downhill. But because of spatial autocorrelation, you don't go downhill on hard ground in an instant from going uphill in soft ground. It's going to be somewhat related. And so we could very, very accurately predict and effectively get on every square meter exactly what our target rate is. So it's things like that, or innovations like that, a big part of my farming history. In 2011, I started working with a friend from college to take the show on the road effectively, kind of grow what we were doing in a very significant way. So we raised funds to invest both in farmland and in early stage technologies, 2 very different asset classes, but highly synergistic based on our experiences. He had a career in venture capital in Silicon Valley, and had been backing and building technology companies at one of the leading firms. So this is what our farmland portfolio looks like today. We've got farms in Louisiana, Arkansas, Mississippi, Wisconsin, Montana, Idaho, Washington, and Oregon, growing all the major commodity crops and several different permanent crops. And we also invest across biotechnology, software, hardware, and food and nutrition. So we've got over 30 companies now. I think 29 of them are listed here. One of the things that's most interesting from a financial standpoint about investing in these is how time factors are so different. Farmland often trades at 2% cap rates these days. So capitalization rate is an inverse of a multiple, an income multiple. Effectively, there's an expectation in farmland that incomes are very stable, and distant incomes are valued very highly. In early stage venture, return targets are often 40% IRR, can be higher. We are looking for at least 10 times your money on early stage investing. And times like these, where we've had a significant increase in the risk-free rates, and also risk premiums have expanded significantly. For companies with very distant cash flow expectations, the cost of raising money today is extremely high. As we think about automation and robotics and machinery, it's interesting to look at across the United States, as a lot of the kind of technologies that I worked on early in my career have become commercialized and have become pretty standard. What's been the effect of that at an aggregate level on kind of costs and productivity in the United States? And it's rather surprising. Machinery costs have gone up much faster than inflation on a per area basis, but also even on a per unit of productivity basis. So we've only been increasing crop yields among major crops at about 1% per year in the United States and in recent times. And machinery prices have gone up over 4% per year. So it's very different from what we see in other areas of automation, where you expect massive increases in productivity and massive declines in cost. We haven't seen that. One might presume that the machinery price is going up, that cost is going up, but other costs are going down. Effectively, what we see here from fertilizer prices and seed prices is very much kind of driven by the pricing component of those inputs and not by utilization rate. So there's been a little bit of an improvement in fertilizer and seed use efficiency and chemical use efficiency with more automated machinery, but not very much. The success has really been in making the farmers' lives more comfortable. And so adoption rates are very, very high, and people don't go back. So, and they're willing to pay a lot. And the companies that produce the automated machines have been doing very well. Stockholder returns have been solid. But as we look at fall line at automation, we're looking for not only kind of what is commercially viable, but what can really have an impact on land use efficiency and other major inputs. One of the observations that I've had in farming is that in the core of the Corn Belt, which is the largest farming area of the United States, there's been very little dynamism with respect to prices of commodities. So I farmed when corn was $1.50 and when corn is $8, and over that time, the recipe, seed, chemical, fertilizer, machinery, fuel, hasn't changed very much. The farms, if you kind of went back in time over these different time periods, you'd see the fields would look the same. And as you look at from farmer to farmer, they also look very similar. People don't really interpret the recipe very differently. And a lot of the ideas we have of improving farms are things that may have, they may be systems that you would want to employ in a very low cost scenario, very high cost scenario. And it's useful to think about what is the value, what's the option value of being able to have switches that you can turn on and turn off as price goes up and down. This is not something we see people do in agriculture pretty much ever. But it's pretty much everything that matters financially on a farm can be, is embedded in the cost curve if you kind of go through and build these cost curves. So if we think about total cost curves generally, you put how many widgets you're going to make on the horizontal axis and what the cost is on the vertical axis. For this exercise, it's useful to flip that. So effectively what we're doing is using empirical data to look at, for different farm budgets, when a farmer spends a certain amount, and that's optimally used for kind of the ex ante expectation of what yield he's going to get. How does that vary at different price levels? And then we can fit a curve to those different points. And this would be a pretty representative curve for Iowa, where we've got, again, it's the production cost on the horizontal axis and the productivity on the vertical axis. We farm in Mississippi, where you see farmers grow some different crops, major commodity crops with a similar machinery set, but with kind of different levels of intensity, and farmers approaching those at different levels of intensity. It's a much wider spread. But we also see an opportunity there for double cropping, a way of intensifying that in certain economic conditions may be relevant, in other economic conditions may not be. But there's less empirical data for what that curve looks like. It's more based on kind of a structural knowledge of what the agronomic resources are and what the genetic resources are. So it's a highly desirable thing to do, not only because it's a way to massively increase the output of the farm, but these tend to be, flat farms with a lot of soybeans and cotton, kind of low biomass crops that are heavily tilled, and in the winter they sit open, and we get about 60 inches of rainfall. So huge amounts of rainfall, a lot of that falling in the winter, which is very damaging to the soil. what we're interested in doing is growing canola on those farms in the winter, and wheat on those farms, which kind of have different levels of intensity, different cost curves, different return expectations. But we can model out based on our structural knowledge of the farm, what we would expect that to look like, and then and build these curves. So these curves then can help us answer how intensive should we be based on different prices. So first, looking at the Iowa curve here, now we've switched the vertical axis to dollars in net operating income. So we're taking that total cost curve and multiplying times price, subtracting cost, and getting this net operating income. So obviously, as price goes up, income is going up, but also the peak of that curve, where marginal cost is equal to the commodity price, is shifting very slightly to the right. Not very much though, which explains why farmers are pretty much doing the same thing, neighbor to neighbor, and also throughout time. If we look at Mississippi, if our kind of estimations of these curves are correct, it's a much wider sweep. And it's important to also look at operating margin. So in this kind of a graph, operating margin emanates from the origin, and we can see here 15, 20, 30%, 40%. So there will be different thresholds that operators have. But what's most notable here, and you probably see it best on these monitors to the side, where the faded lines are kind of hard to see up here. In Iowa, we cross those lines of margin very, very steeply. So you kind of know where, regardless of what your kind of thresholds are, or your kind of subtle interpretation of that curve, it pretty much puts you into one narrow spot. That net operating income follows these lines of operating margin over very, very long distances across the cropping intensity in Mississippi. And so, several different implications of that. One, subtle differences in a farmer's expectations can make a very big difference in whether they farm a 30 bushel soybean crop, very low intensity, or whether they're getting going for 120 bushel wheat crop followed by a 200 bushel corn crop, much more intensive. And also the impact of technology is much higher. So as we solve problems, as we shift that curve, there's a much bigger impact. We can have massive changes on the cropping system. And then we can also look at call option pricing to look at for each one of these different price scenarios, what incremental units of productivity is generated at different prices, what's the value of the call option at that price, and then we can kind of sum those up, and that represents the value of the land for rental. And so we can do that for both areas, make a comparison, because land in Mississippi is half as expensive as Iowa, and we were denominating by area. We kind of need to double the size of that, and effectively what we come up with is $312 an acre in Iowa, and $1,010 for 2 acres, so $505 an acre in Mississippi would be kind of the value of that land if that curve is correct. Now, actually implementing that curve in double cropping is a bit challenging for a few reasons. The heavy rainfall makes it difficult to get heavy machinery across the land, and so being timely is incredibly important in double cropping, and these agricultural machines will weigh 50,000 pounds, 60, 70,000 pounds. But it's also encouraged people to spray by airplane. So this is a picture in Mississippi of kind of the effect of spraying by airplane. All these border areas are, not only do you have spray drift, but completely denuded. And so that, all of that runoff is just running off the edge of the field, carrying sediment, seed, fertilizer, chemicals are going with it. And so spraying by airplane causes another problem. People tend to grow genetically modified crops in these areas that are all resistant to the same chemical. So if you spray by airplane, you hit your neighbor's field, it doesn't matter that much to the crop. They're resistant to dicamba, glyphosate. But a lot of the winter crops we want to grow aren't resistant to those herbicides and would get killed. So not only does spraying by airplane lead to kind of resistance, denuding of these border areas, but it also prevents us from improving the cropping system. So this is something that's kind of several facts about spraying by airplane. Aerial spray droplets are downsized by shear, so you get smaller droplets. That's been studied. Small droplets drift further. It's you think of sedimentation rates both in marine applications and in aerial applications, and proportional to the square of the droplet diameter. Just kind of a canonical fluid dynamics there. Wind speeds increase with height, and aerial release height is very, very high. And aerial applicators generally don't even try to avoid spraying the border areas, so they all get denuded. And this all kind of compounds to another problem with resistance. One of the common studies in weed science is to take 100 million seeds, plant them out and spray a full rate of a herbicide, see how many survive. Typically they'll all die if they're not resistant, and then put on a sublethal dose and take the survivors, cross them and do that for several years. And for most of our herbicides, after 3 years, we have populations that are resistant to between 2 and 8 times what the herbicide is. And that field vegetation border is very important, stops more than 95% of erosion. So we really want to maintain that as well. So one of the things I'm very passionate about, improving spray application, is a move to spraying by air. This is it's something that's done with kind of small machines in certain parts of the world, has really kind of grown since 2018, where it was there was almost no market for it. It's by 2020 more than $1.5 billion of small drones used in spraying. But there had not been any machine that in the United States was built for kind of the heavy lift commercial applications that we have. And so one of our investments was with a company called Guardian Agriculture. And just a couple of weeks ago, they became the first eVTOL company to be permitted by the FAA for any kind of commercial activity in the United States. So there's no heavy lift eVTOL company that is besides Guardian that is licensed for cargo or people or spraying or anything else. Here's a video from one of our farms in Wisconsin, and kind of one of the early. A lot of the innovations of this machine are really around the safety systems, propulsion system. There's the patents on the spray system as well. And in the powertrain, it's really the battery is the key thing. So one of the reasons why agricultural machinery is so expensive today is that failure rates are incredibly high. And I think there's been a massive underestimation of the effects of complexity. So kind of anyone who's done anything in reliability engineering is kind of familiar with the canonical application of the Weibull distribution in characterizing failure rates and the various parameters that go into that. And it's the shape parameter that is really describes a characteristic of whether we have a infant mortality, constant failure rates, or wear out failure rates. And if we think about kind of a lot of ag machinery that we would have had, several generations ago, plowshares and things like that, like there's not a lot of infant mortality to things like this. There's they're wear out failures. They don't have a bad line of code that gets tripped up at some point. And so most of you are familiar with kind of the bathtub curve that would describe kind of the combination of different types of components with different beta parameters within a system. And so much of reliability engineering is pretty intuitive. Concepts around redundancy, that's your most, improving your most reliable component is what gives you the best reliability. That's very intuitive. And when you're in series, improving your least reliable component gives you the biggest increase in productivity. That's very intuitive. I think what's not very intuitive is the incredible effect of combining components that have low beta. So, what's described here is if we have a stack of components, imagine stack A and stack B, and they both have lifespans of 100 years. But this stack of components has a very, very low beta. The stack has a very high beta. If we combine these with the high beta, we may go from 100 years to 99 years. And you keep adding them on, you go down to 80 years, 85 years. With low beta, you can go from an expected lifespan of 100 years, median, suddenly to 2 years, to 5 minutes, and you get systems that just fundamentally don't work. That like you just have huge startup failures, and that's very characteristic of agricultural machines today. It was some interesting comments yesterday about robots and marine applications. Like, we need them to work, and this is something that I think we hear a lot from farmers. As it relates to the drone I was showing earlier, I'll just highlight kind of one example of the approach. So, one of the keys in that type of application where they're not long flight times, you're looking at dispensing large amounts of material pretty quickly, and then you want to get back and dock immediately. So it could be 2 to 7 minutes kind of flight times. So you're optimizing around that. And so the concept of either how you switch batteries or charge batteries becomes really important. And fundamentally, as we kind of look at the overall reliability and what we needed to do to kind of hit the safe levels of safety that we needed to be at, trying to get a connector in a swapping battery kind of scenario to be reliable enough is something that we didn't feel like it was as achievable as we couldn't meet our needs. And so we designed a very, very fast charging battery. So we can charge in the amount of time it takes to fill. And we charge at rates that are about 5 times faster than a Tesla supercharger. And so that's one of the key areas of innovation there. Okay, and I'm going to stop there for questions. I tried to rip through here fairly quickly.